Hey everybody, I'm going to take you through the first couple examples here in part 2. First thing we're going to look at is, it says label where hot and cool mantle material would be. Draw an arrow showing convection currents in the mantle. So as we know from our study of the layers of the earth, the crust is cold. As you get towards the center of the earth, it gets hotter and hotter. The core is very hot. The mantle has this unique ability in the upper mantle to move. It's got the ability to flow. And so what happens is that core is going to heat up the mantle, causing it to get less dense, and it will rise like this. Now when that mantle, that warm mantle material reaches the crust, it's going to start to cool down. And as it cools down, it's going to get more dense, and it's going to sink back down towards the core. And this process will continue. It's called a convection current. Hot rises and cold sinks. Okay, now this happens in many places around the world. And I'm just going to draw another one on the right side here. So the core is going to heat up the mantle, causing it to rise. As it hits that cold crust, it's going to get cool, it's going to get more dense, and it's going to cause it to sink back down towards the core. And we get that circular pattern called a convection current. Let's take a look at image number 2. Okay, here in image number 2, what we're supposed to do is label the lithosphere and asthenosphere in the diagram. Draw arrows on the crust in the boxes showing how the lithosphere moves. So first thing we're going to do is we're going to label where is the lithosphere and the asthenosphere. The lithosphere is this dark brown area that makes up the crust and the upper part of the mantle. The asthenosphere is this area in the light brown and the asthenosphere's got this ability to flow. It's kind of like a plastic-like material. It's got the ability to move a little bit. Unlike the lithosphere, which is very solid and brittle, the asthenosphere's got the ability to flow and to move. Okay, so this motion in the asthenosphere can make the lithosphere move with it. It drags it depending on which direction the convection currents are moving. So if we take a look at this first part in red, I see the convection currents are getting heated up. As they hit the crust, they cool down, but it's got this motion towards the left. It rises up and it moves to the left. That tells me that my crust is going to be moving towards the left. This convection current right next to it is going to be moving up and over towards the right. That tells me that it's going to drag this crust over to the right. So I know that my crust is going to go that direction. So this is what we call a divergent boundary. It's where the two pieces of crust separate or divide. Okay, let's take a look at this next one here. Okay, now we've already looked at the motion of this plate right here. We know that it's moving this direction. I can see that by this convection current that's moving to the right. So I know that it's moving this direction. Now this one over here, I see that it's rising and it's moving towards the left. So it's got this left movement. It's going to drag this piece of crust this direction, and those plates are going to collide. So I got a left moving plate right here. Those plates come together. That's called a convergent boundary. They converge or collide. Okay, taking a look at the next one. Okay, I know that this plate is moving up and over to the left. So I'm go ahead and put in my arrow. I know that one is moving left. And I know that this plate on the right, I can see that it's moving up and it's moving over towards the right. So it's going to have a right motion. It's going to drag this piece across to the right in that direction. So these plates are dividing. Again, that's a divergent boundary. This is happening under the water. This is a mid-ocean ridge where the plates are separating. So in all three of these examples here, okay, this is my plate boundary right here. And it's where these two convection currents come together, that tells me what kind of plate boundary it's going to be, if it's going to be dividing or if it's going to be converging together. Okay, let's take a look at the last one. Image 3. Draw convection currents on your own based on the motion of the plates. Use red arrow for warm mantle material and a blue arrow for cool material. Each image should have 2 full convection cells. Okay, so I'm going to grab my warm, my hot, and the orange is going to be my mantle, and if I can just imagine that underneath these would be the core that's going to be really hot and heating up the mantle. So I can see that these plates, I can see one plate moving to the left, one plate moving to the right. So I know that my warm mantle that's coming up here is going to be curving to the left, dragging that plate to the left. As it cools down, it's going to sink back down, and there I got my full convection current.
Please call 37506. Chris Caulfield, please call
Okay.
37506.
Now this plate on the right is also moving to the right, so it's going to be moving like this, dragging that crust to the right to complete the convection current. As it hits that cold crust, it's going to get cold and sink down. There's my 2 full convection cells for that image. Okay, now let's take a look at the next one. Okay, so here I have one plate moving to the right, this plate colliding with it, and it looks like this plate is being subducted or going underneath the other one. So let's put in our convection cells for those. I should have 2 full convection cells. So I know that this material must be rising and curving to the right. And as it cools, it's going to sink back down. This convection current over here, I know that it must be rising and going to the left, judging by these arrows. And as it cools, it's going to sink down like that. Okay, so those are our 3 examples. If you have any questions, just message your teacher.